AC circuit components, also called RLC circuit. This is due to the focus of this chapter on the resistor, the inductor and the capacitor. When we look at a resistor, we know that the resistor has a value that is measured in ohms. When I pass current through this resistor, I will develop a voltage on that resistor. Now, in grade 10 you learned that the size of the voltage is dependent on the size of the current that flows through that resistor. So if I take my resistor and I apply a sine wave as a voltage onto the resistor, I will get a sine wave as a current on my resistor. We also know that the current flow in the resistor is equal to the voltage across the resistor divided by the resistance of the resistor. Now, in order to get this sine wave, what we do is we represent it as a Phasor diagram. Now we know that in order to generate a sine wave, we rotate a conductor in a magnetic field. Now as it rotates, we will see that my voltage, which is my big force, and my current, which is my small force, both occur at the same time. So as this rotates, it is going to generate those two sine waves. Next component is the capacitor. The capacitor has a value which is represented in farads, usually millifarads or microfarads due to the small size. That farads is the ability of the capacitor to store a charge. Now when we look at the construction of the capacitor, we see that in the middle over there we have got a insulating material called the dielectric, and that stops current from flowing through it. But as I supply a signal onto this capacitor, electrons or current is going to flow in on the one side and charge that plate negative, and it's going to force electrons on the other side to leave, which is going to charge that side positive. Now if I reverse the polarity of the supply voltage, what's going to happen is current is going to flow in this side, causing this plate to now discharge and become negative, and that plate is going to discharge and the electrons are going to leave there, and that's going to cause the plates to become positive on that side. Now we cannot use Ohm's law on a capacitor as is, because the resistance, actual resistance of a capacitor is infinite. And in maths you learn that if you divide something by infinite, you get 0, and that's not the case. So we realize that once we apply a sine wave or a signal onto a capacitor, what happens is the following. It develops a capacitive reactance, which is an apparent resistance caused by the charging and the discharging of the plates of that capacitor. It's been discovered that that reactance of the capacitor is equal to the inverse of 2 pi f, which is the angular velocity which causes the sine wave, multiplied by the capacitance. What this means is the larger my frequency is, the smaller my capacitive reactance is going to be. Now if we look at the waveforms that is generated and the phasor diagram that is generated, if I apply a voltage, if I allow a current to flow in my capacitor, what's going to happen is we're going to get a lagging voltage on my capacitor. That lagging, remember it's a rotating entity, that lagging is caused by the charging and the discharging of the plates. Looking at the phasor or the wave diagram, we see that as my sine wave as current is applied to my capacitor, it will generate a signal in the voltage that looks like that, with a 90-degree phase shift. Okay, that 90-degree phase shift is the reactance of the capacitor to the alternating current. Once I've determined my capacitive reactance using this formula, it is easy to calculate my current flow through the capacitor, or the voltage of the capacitor, using Ohm's law, and that is XC. So IC, or the current through the capacitor, equals the voltage of the capacitor divided by the capacitive reactance, which is the apparent resistance of the capacitor. When looking at the final component, which is my inductor, I know that it is usually measured in a Henry value. Now that Henry value is the ability for this coil to generate an EMF within itself when it experiences a change in current. Again, it's a reactive component because the inductor is nothing more than a conductive wire that's wrapped around a core. Now, in theory, that means I should have 0 ohms, or almost 0 ohms on my coil. But if I apply Ohm's law to my coil using the almost 0 ohms there, what is going to happen is I'm going to get almost infinite current. So we've realized what happens is when current flows through the coil, each loop generates its own magnetic field. The size of that magnetic field is dependent on the size of the current that's going to flow through that coil. Now, because those loops are so close together, there's no space for that magnetic field to expand. Because there's no space, those magnetic fields are pushing against each other, and because the magnetic field can't expand, that resists the current that's going to flow in my coil. The inductive reactance is equal to 2 pi f, which is the angular velocity, again like with a capacitor, multiplied by the inductance. So as my frequency increases, my inductive reactance is also going to increase. If we look at the phasor and the wave diagrams for the inductor, if I supply a current flow through my inductor, what happens is it is going to generate a voltage that is 90 degrees leading, whereas the capacitor is 90 degrees lagging. That is VL, and the result being, if I draw a wave diagram, I see that my current, which is the sine wave, and the voltage which is generated is going to be 90 degrees out of phase. that's VC. Okay, again, this is because of the rotational force, the rotating entity that we get over there. Okay, so to summarize, if we compare the voltage and the currents, because this is a series circuit, because all these components are connected in series, we are going to have a constant sine wave for the current. The voltage, on the other hand, is going to separate over each individual component in accordance with Kirchhoff's voltage law for series circuits. If we look at the effects that a range of frequencies is going to have on my RLC components, we can represent that as a graph. These are my range of frequencies, and we will see that my inductor, because of this formula, XL equals 2 pi FL. So as my frequency increases, I will have an increase, linear increase in my inductive reactance. The capacitor will have a non-linear decrease due to the range in frequencies, and my resistor will remain constant because frequency has no effect on the ohmic value of my resistor.